Hello everyone, welcome to this third lecture on waves. In this lecture we will talk about one very important principle that is known as the principle of superposition of waves. And the principle of superposition of waves, uh, we have whenever two or more sets of waves passing through a same medium and cross one another, in that case they behave independent of each other. It is as if the first wave which is crossing the second wave in the same medium at the same time, in the same location, it doesn't care about the presence of the second wave. They completely behave independent of each other. All right, and the net displacement of a particle at that particular location is equal to the algebraic sum of the individual displacement due to all the waves present. All right, so I will explain this pictorially in a while, but mathematically what it is meant, let us first go into that. Mathematically, suppose y1 x of t, because you remember we talked about the wave equation as y1 of xt, that's equal to a sine of uh, say kx minus omega t. So in this case we are just considering, say, y1 x of t be one wave where we have got amplitude to be a1, wave vector to be k1, frequency to be omega 1, and y2 of xt to be some other wave with amplitude a2, sine k2x minus omega 2 t. In that case, if these are the two waves which occur simultaneously, that means at the same time, at the same location, in that case, what will happen to a particle of that particular medium where both these waves are present? Because otherwise what we know, that if this is a particle set and there is a wave or disturbance passing through this medium, then according to the wave these particles will respond and they will vibrate up and down or longitudinal. It depends whether the wave is going in a transverse way or in a longitudinal way. But if there are two or more waves, in that case what will happen? In that case the net displacement of this particle is given by the algebraic sum of the individual waves which are present simultaneously at that location. So if y1 and y2 are the two different waves which appear simultaneously at any location, then the net displacement of the particle will be given by the algebraic sum of y1 and y2. So the total wave, a new wave will be created. Suppose that new wave will have its expression as y, that will be given by y1 plus y2, and the particle will respond to this new function y. It will not respond to y1 only, or it will not respond to y2 only. It will just respond to sum over y1 and y2, and not necessary that there should be only two waves. There could be multiple waves present. In that case, suppose we may have another wave as y3, y4 or y5. Doesn't matter how many waves are there, but the superposition principle says for all of them the net displacement of the particle will be given by the algebraic sum of all of them. So if there are more waves, in that case it will be like y1 plus y2 plus y3 plus y4 plus y5 and so on. So in this case pictorially we can understand this particular thing. Suppose you have got two pulses. This is one positive pulse. Let me say it to be positive pulse. Let me say this to be a negative pulse. They are approaching each other, and somewhat they will meet somewhere in this particular location. At different instances of time we show the behavior of the wave. Suppose at t equal to 0 this pulse was here, this pulse was here. At t equal to 1 they have approached to some extent, and finally they are about to meet. And at t equal to 2 seconds, that means the next instant, they have completely merged up. And while they have merged up, what happens? The positive wave is almost has cancelled the negative pulse. Say the positive pulse has almost cancelled the negative pulse, and ultimately, because you have superposition, so if this region is y, this region will be minus y, so y minus y will be equal to 0. So you relate, I mean, the particles of the medium, because this is a string, the wave is going on a string, say, the particle of the string is not at all being displaced. So particles of the string are completely falling in a straight line. There is no displacement. Why? Because net displacement of the particle will be given by the superposition of y prime is equal to y1 plus of minus y, that will be equal to 0. So there is no displacement of particle, but the wave energy is retained. and because of that, the next instant y is equal to set time t equal to 3 seconds, they once again got separated and travel as previous. All right, so what we see that whenever the waves arrive at the same time at the same location, then only we apply the superposition of waves principle, otherwise not. It is as if suppose this wave is here and this wave is here, you cannot apply superposition principle. Both these waves must come at the same location. All right, then only the principle of superposition will be activated, not otherwise. Now, based upon principle of superposition of waves, there are various phenomena that occur in physics. We can explain over that. So, for example, interference is one such phenomena. Diffraction is one such phenomena. You have got the beats formation, the stationary waves, the modal analysis. There are a lot of things which can be explained based upon the principle of superposition of wave. We will discuss one of them, that is interference, in today's class. But before that, let us further elaborate this principle. Suppose you have got crest. This is a crest, we know, crest of a wave. This is crest of another wave. If the crests they superimpose, then you can see the ultimate wave. Suppose this is y1, crest of y1, this is crest of y2. When they are superposing, then we get the final wave y, whose crest is almost a double in size, because this distance is suppose a and this distance is suppose a. Let us consider that both the distances are a only. In that case, total height here will be equal to a plus a, that will be equal to twice a. So since the total amplitude has increased or shoot up, this kind of superposition is known as reinforcement, or they are said to reinforce. The superposition is said to reinforce the ultimate wave. It's quite contrary to this. If the crest of one wave is superposed with the trough of the second, in that case you have something called cancellation. So in this case you get just a straight line. This will cancel this particular amplitude, and ultimately you will get no displacement resulting. All right, so this example, as you have seen in case of the wave or pulses moving in a string, you can experiment it by yourself also. If you have a string, then two of you can hold the string from both the ends, give it a pulse like this, such that these pulses approach each other, and you will see that for a momentary instance or situation, these, whenever they will approach each other, the string will become straight. All right, and again they will pass like this. You can do this experiment. So this is another example of superposition. This is somewhat complicated waves. Say for example, if they superpose the blue and the red, in that case the ultimate wave pattern you get like this. All right, so if this is y1, if this is y2, this is y is equal to y1 plus y2. That's it. All right, so now let us explain something called interference. Interference is a very beautiful concept, and is a phenomenon by virtue of which there is a modification in the distribution of energy due to superposition of two or more waves. Now remember this particular term. In interference, we have got a modification in the distribution of energy. Uh, Many times when I put this question that whether there is energy loss in interference, people say yes. Actually, this is not correct. Energy is always conserved in the principle of interference, or in the phenomenon of interference. It is only that the energy is redistributed. All right. So in this case, you can see two water waves. Actually, not two water waves, but two sets of water waves. When they superpose, you can see in this particular region, when they merge up, you can see little different pattern. Otherwise, what you see, you'll see that these are circular patterns followed by dips. Then there is another circle followed by a dip region. But in this case, you see somewhat square kind of patterns which have formed. All right, so this particular pattern, or this special category of patterns, they have been formed only because of the phenomenon of interference. So interference, there are various conditions in which the interference can occur, that we will discuss in subsequent slides. But before that, let us go and understand mathematically exactly how interference can be achieved and what are the types of interference. There are two classes of interference. One is known as constructive interference, another is called destructive interference. All right, so mathematically we will understand that. Let us consider two different waves, y1 and y2. There is a slight mistake, this will be y2. So let's say y1 is equal to a1, the amplitude a1, sine of kx minus omega t, and y2 has got slightly different phase as compared to y1. So I have retained the k, that means wave vector, quite similar to the y1, the angular frequency quite similar to y2, y1, but only thing I have varied is a delta. Means both these waves, they are almost same, but only thing is that the second wave is having a delta phase extra than the first wave, and also alongside the amplitudes are also different, slightly different by the way, not very highly different. All right, so what will happen? Principle of superposition says that whenever both these waves appear in a same location simultaneously, then we can write y2 is equal to y1 plus y2. Clear? So there is something called this particular formula. You must remember that sine of a plus b is equal to sine a cos b plus cos a sine b. This formula must be remembered. This trigonometric identity is something that we will use here because we have got sine function. So what actually we can write? We can write y to be is equal to a1 sine of kx minus omega t. This is nothing but y1 itself plus y2, and in case of y2 what I have done, uh, y2 is equal to say a2 sine of kx minus omega t plus delta. So I have separated these things into two terms. I have separated this into one term and this to be the other term. In that case I kind of have the formula which is similar to sine of a plus b formula. So in that case I can write it a2 sine a kx minus omega t cos of b plus cos of, by the way this is common, cos of a sine of b. This is quite similar to this particular formula. If I, and in this case I have just put this thing directly, and if you do that, then you can see that there is a sine of kx minus omega t, and here also you have got a sine kx minus omega t. So you can just take these two things common. So sine of kx minus omega t, if you take common, you will retain with one term from here a1 plus a2 cos of delta. And similarly you can take cos of kx minus omega t, in which case you will have a2 sine delta together. All right, now we will make a little bit of mathematical manipulation here. We will just simply say that a1 plus a2 cos of delta, this particular term, let us say this to be a cos of epsilon, and this term a2 sine delta, let us say it to be a sine of epsilon, and if you put them into this equation, you will remain with y to be is equal to some capital A sine of kx minus omega t cos epsilon plus cos of kx minus omega t sine epsilon. And very beautifully you see this is once again a formula which is like sine a cos b plus cos a sine b, which eventually is sine a plus b, and ultimately I can write y is equal to a sine of kx minus omega t plus epsilon. Now, although I have written this, I do not know what is actually the value of a and what is actually the value of epsilon. Okay, so that we will take out in the next slide. But before that, what we have observed here, that the ultimate wave or the final wave y, which we have got after superposition of y1 and y2, is nothing but the resultant. That means that's what has been explained here, that thus the resultant is indeed a sine wave of amplitude a and a phase difference epsilon with the first wave. It is quite similar to the first wave. See, a sine of kx minus omega t, but there is only one epsilon coming in here. So it is little different than the first wave. And how exactly it is different? That it is different by a phase constant epsilon. And of course the amplitude is not a1 or a2 in this case, amplitude is a, and how a is related to a1 a2, that we will see in the next slide. So here we can see so these relations I'll write once again, which I assumed a1 plus a2 cos of delta to be a cos of epsilon and a2 sine of delta to be a sine of epsilon. I'll write them once again here. So that's what I have written it here. So these are my two equations, say 1 and 2. In that case, squaring on both sides. So if you square these equations on both the sides, say I want to do this 1 square plus 2 square, that implies what? A square cos square epsilon plus a square sine square epsilon, which is equal to a1 plus a2 cos delta square plus a2 sine delta whole square. But interestingly, in this case, if you take a square common, you will remain with a term called cos square epsilon plus sine square epsilon, and this side it will remain the same. But cos square theta plus sine square theta is equal to what? This is equal to 1. So you will remain with only a square in this case, and this right hand side will follow. So from this right hand side, what we can get, that see here a square, that is why I have written it here, squaring, actually it should be squaring and adding. Please whenever you make note, uh, write this thing, squaring and adding on both sides, we get a square, that's equal to a1 plus a2 cos of delta whole square plus a2 sine delta whole square, and ultimately from here you can eventually get a square equal to a1 square plus a2 square, because there will be one term called cos square delta plus sine square delta, which if you take a summation, once again you will have a term called cos square delta plus sine square delta, which is again equal to 1. So you will remain with a2 square, and alongside you will remain with twice a1 a2 cos of delta, which will come from this particular term. So a is equal to square root of a1 square plus a2 square plus twice a1 a2 cos of delta. So ultimate amplitude of wave A after superposition of two waves which are having amplitude A1 and A2, the final amplitude is given by this relation, square root of A1 square plus A2 square plus twice A1 A2 cos of delta. What was delta? Delta was the phase difference between the initial waves y1 and y2. Alright. What is epsilon in that case? As in this case we have just taken a square and added them. Now I'll just divide them. That means 1 by 2, or rather let me do it like 2 by 1. In that case what I'll do, a sine of epsilon divided by a cos of epsilon, which is equal to a2 sine delta divided by a1 plus a2 cos delta. So a gets cancelled. Sine epsilon by cos epsilon means sine theta by cos theta is nothing but tan theta. So tan epsilon you will get, and in this case you will remain with a2 sine delta divided by a1 plus a2 cos delta, and ultimately I can write epsilon is equal to tan inverse of a2 sine delta whole divided by a1 plus a2 cos delta. So this is what is my epsilon. So see how beautifully we have evaluated both these unknown parameters a and epsilon, because in the previous slide, as already I said, these parameters a and epsilon are unknown, but now we know what is the form and how they are related with a1 and a2, and of course delta. So that's what is the ultimately interference of waves that has given you. But now question is, how would you know that when there are two types of interference, basically, as already I have said, constructive and destructive. So how they are to be obtained from this particular expression? Let's see that. So constructive interference, so this is the case 1, which is constructive interference. If delta is equal to 0 or twice pi or 4 pi or 6 pi, that means it goes as even multiple of pi. So even multiple, how do we write? Even multiple, we write it as twice n of pi, where n is equal to 0, 1, 2, 3, etc, etc. So if delta is having this kind of form, that delta is equal to twice n pi, even multiple of pi, in that case cos delta is equal to plus 1. Why cos delta equal to plus 1? If delta is equal to 0, see cos of 0 is equal to 1. If delta is equal to twice pi, cos of twice pi equal to plus 1. If delta is equal to 4 pi, cos of 4 pi is equal to plus 1. So if it is an even multiple of pi, for all those values of delta, cos delta will be equal to plus 1. If you put cos delta equal to plus 1 into this expression of amplitude, final amplitude, then this cos delta you'll have to put as 1. So you'll remain with a1 square plus a2 square plus twice a1 a2. So that's what I have done here directly. And this is nothing but, if you remember, the formula of square root of a1 plus a2 whole square. So since there is a square and square root and there is a square, so they cancel each other and ultimately you get a1 plus a2. So that is, the net amplitude is equal to the sum of individual amplitude, and this type of interference is known as constructive interference. This is a case of reinforcement superposition, all right, where ultimately the total energy is enhanced. And see, in case of constructive interference, the crest of one wave coincides with the crest of other. The intensity of a point where this type of interference occur is maximum, and the point is known as the maxima. So wherever, in which point this particular type of interference occur, that point is known as the maxima. And the condition is what? That condition is that delta should be equal to even multiple of pi, twice n pi. Now there is a very important relation which is called phase difference and path difference. Path difference means what? Suppose you have got a wave. This is a single wave and there is one more wave. Okay, now even definitely you can see that this wave is little longer than this wave. Now if I ask how long this wave and this wave, how they are different? They are different by one wavelength lambda, because it has got only one cycle of oscillation. This has got two cycles of oscillation, so one cycle is extra. And how many wavelengths are there per cycle? Lambda. So that is why the difference between the paths of these two waves is equal to lambda. That is what is the meaning of wave, path difference. So if you know the path difference, you can easily get the phase difference, and vice versa. If you know the phase difference, you can get the path difference. The formula is this particular formula you should always remember, that phase difference is equal to twice pi by lambda into path difference. All right, so what is delta? Delta is the phase difference. So delta is equal to twice pi by lambda into path difference. Let us say it to be x. In that case, in place of delta, I will put twice n pi, and here it is twice pi x by lambda. So this pi gets cancelled, 2 gets cancelled. You remain with n is equal to x by lambda, or x equal to n lambda. Or I just want to write it in a little different way. I have just multiplied a 2 and divided by 2 over here, so that I can get twice n into lambda by 2. So constructive interference, or for constructive interference, the path difference between two waves should be an even multiple of lambda by 2. All right, when two waves are there, if the path difference between the two waves is an even multiple of lambda by 2, then we can guarantee that the interference is a constructive type of interference. There will be reinforcement of energy, reinforcement of intensity. All right. Quite contrary to this, there is something called destructive interference. And destructive interference means, if you have got the phase difference between the two waves to be an odd multiple of pi, that means twice n plus 1 pi, see, pi, thrice pi, 5 pi, 7 pi, or 9 pi, or 11 pi, like that, if it goes, such that I can write as twice n plus 1 pi, where n is equal to 0, 1, 2, 3, etc., then cos of delta will be equal to minus 1. If cos delta equal to minus 1, then the net amplitude is given by a1 square plus a2 square minus twice a1 a2, because there was a cos delta term. Cos delta is equal to minus 1, so this minus sign is there, and this is nothing but, we know, a1 minus a2 whole square, and eventually ultimately we get a1 minus a2. So in this case, what happened? The net amplitude is equal to the difference of individual amplitude. See, the two waves which were superposed together, they had amplitude as a1 and a2, and final wave, because of destructive interference, the final wave has got an amplitude of a1 and minus a2. All right, so it is the difference of amplitude of the two individual waves. So in the case of destructive interference, what happens? The crest of one wave is superposed or coincides with the trough of another wave, and in that case, following the same principle, that phase difference equal to twice pi by lambda into path difference, if you put that, you will finally get x equal to twice n plus 1 lambda by 2. So that means for destructive interference, the path difference of two waves should be an odd multiple of lambda by. So if the path difference between two waves is an even multiple of lambda by 2, then you get a constructive interference. If the path difference of the two waves is an odd multiple of lambda by 2, you get destructive interference. In case of constructive interference, there will be reinforcement of intensity, or intensity will double up or increase further. And if you have a destructive interference, there will be decrement of intensity, or resulting intensity may even become zero. All right. So we will see that pictorially in next couple of slides. But before that, this is a slide which is devoted to the understanding of path difference and phase difference. The slide is quite self-explanatory. I wish you please go through this particular slide by yourself and you will understand. Just one example I want to give. Suppose a question may come that path difference of two waves is lambda. What is the phase difference? How do you find it? So in that case, you will find it in this way. Phase difference is nothing but twice pi by lambda into path difference, and already has been given that path difference is lambda. So lambda lambda gets cancelled, phase difference becomes twice pi. It may be given opposite also. Suppose the phase difference of two waves is given to be pi. What is the path difference? This particular formula has to be applied once again. Alright. So I hope you will understand by making a self-reading of this slide. Now let us go for the conditions of interference. What are the conditions of interference? That the two sources of waves must emit continuous waves having same frequency and wavelength. The frequencies and wavelengths of these two waves should be equal, and continuously they should come. It should not be in a pulsed form. It should continuously come. The amplitude must either be equal or nearly equal. Means although we have considered the difference in amplitude of the two waves, I considered the amplitude of y1 to be a1 and y2 to be a2, but this difference should not be very large. Okay, y1 and y2, they should have amplitude almost nearly equal or completely equal. Then third, the two sources should be situated close to each other. It should not be that one source is here, another source is 1 kilometer away. In case of acoustic interference I'm talking about, such should not be the case. The two sources should be very close to each other. Okay, fourth point, which is very important point, the two sources should be coherent. Many a time people confuse this term coherent. What is meaning of coherence is that the waves coming from two different sources should have a constant phase difference. Okay, as already I have considered that y1 is equal to say a1 sine of kx minus omega t, and y2 I have considered to be a2 sine of kx minus omega t plus delta. So this is the phase difference between two waves. So this phase difference should remain constant forever and ever. It should not change with time. All right. So this is something which is a condition of interference, and very very important conditions. All right. Then hopefully this is the final slide. Intensity distribution, as already I said that for constructive interference, let us consider the amplitude to be same, and let's say a1 equal to a2 is equal to small a. In that case, what is the total amplitude? A, already we know that a1 plus a2 for constructive interference, so I can write a plus a, which is equal to twice a. Now intensity, how do we express it? Intensity is expressed as square of the amplitude. So for the resulting wave, square of the total amplitude is intensity. So I is equal to a square, which is equal to 4a square, because a is equal to twice a. If you square it, then 2 square is 4, a square remains a square. For destructive interference, a is equal to a1 minus a2, so a minus a, which is equal to 0, and ultimately the intensity is also 0. So those positions where destructive interference is there, the intensity is 0. Those positions where there is constructive interference, you have got intensity to be 4a square. So in the side figure, this particular thing is very clear. So whenever you see the phase difference between the two waves is 0, the intensity is maximized. So this position is known as a this is a maxima. And again, when the phase difference is pi or minus pi, the intensity falls off to 0, minima. Again, when the phase difference is twice pi c or minus twice pi, the intensity is maximum. So these are the locations of constructive interference. And as already I told you in a couple of slides back, that whenever the phase difference between two waves is twice pi, 0, 4 pi, 6 pi, etc., that means even multiple of pi, in that case you get constructive interference. From this figure also you see the same thing. Say for twice pi, 0 or 4 pi, you see you get constructive interference. That means intensity is maximized. How do you know constructive interference? When intensity is maximized, that is a constructive interference. If the intensity falls up to 0 or minimized, in that case it is a destructive interference. So it destroys the intensity. So see, whenever the phase is odd multiple of pi, either thrice pi, 5 pi or pi, then these are the locations of destructive interference where intensity falls up to 0. Alright, which is a direct proof of whatever we have discussed till now in today's lecture. Alright, so please go through this slide and we will come up with some new topics in next class. Thank you.